Let's talk about another kind of memory corruption that takes advantage of how processes dynamically resolve shared library functions at runtime. In this video, we're going to talk about what happens when entries in the global offset table are corrupted. Now, before we can talk about the global offset table, we first need to have a quick refresher on static and dynamic linking. Recall that linking is how we relate our executable binary to any shared library functions that we may want to call into. There's two ways that we can link our binary. The first is by creating a statically linked binary. When we create a statically linked binary, what's happening at compile time is we are copying the assembly instructions from the shared object or from the shared library into our executable. This means that all of the assembly instructions that are necessary to run our program are in one big binary blob. That is kind of a trade-off, though, because it's one big binary blob, so it takes up more space on disk. If every executable were a statically linked executable, there'd be a ton of code duplication, because we'd be copying all of that shared functionality into every single binary. The second downside to a statically linked binary is the fact that we have copied the implementation of the function at compile time. And so if at a later point that shared library gets an update and the code changes, we don't benefit from that with our statically linked binary. If we wanted to update our statically linked binary to use a newer implementation, we would have to recompile and rebuild our statically linked binary every time. For those reasons, the kind of default executable is a dynamically linked binary. A dynamically linked binary does not copy the assembly instructions into the binary. Instead, at all of the call sites where we would call into a shared library function, a small stub, a placeholder, exists. And this placeholder exists so that at runtime, when it's executed, the loader will dynamically resolve the functions that it needs. It'll figure out where that shared object is and call into it at runtime. Let's take a look at static and dynamic executables on the Dojo. So I'm going to start up the GOT corruption demo. Everything that we need is going to be located here in the challenge directory. We see we have a number of build scripts and a number of source files. The first thing that we're going to look at here is the static example source. It's not a very interesting program. If we take a look at mains, it's going to call puts, printf, and then puts again. Now I'm going to compile this as a dynamically linked executable. The -o is the output. I'm not specifying anything special to make it dynamic. That is the default behavior. And so now we have an executable named dynamic. Now I have a script here called build static. If we take a look at it, it's doing the same thing, calling GCC, except it's using the -static argument. And so if we were to call that on our same source, I now have a static binary as well. Now I can know that these are static and dynamically linked executables by running the file command. So if I run file on dynamic, I see I have a 64-bit executable and it is dynamically linked. Conversely, if I run the file command on the static binary, we have a 64-bit executable that is statically linked. Another way that we can tell the difference between a statically and dynamically linked executable is by running the LDD command. LDD takes an executable and it lists all of the shared objects or shared libraries that are needed in order for this program to run. So if I run LDD on the dynamically linked executable, we see here that it needs Linux VDSO as well as libc.so. These two are very commonly needed in virtually any binary. For instance, if I were to look at user bin cat, we see these same three shared libraries are needed at runtime in order for the binary to run. Now, if I were to run LDD on the static binary, it just says this is not a dynamic executable. The static binary doesn't need anything else on the system in order to run. That's what a statically linked binary is. Now, let's use GDB to take a quick look at these stubs. So I'm going to run GDB on static. We'll disassemble main. We'll set a breakpoint at main plus 15. This is the location where puts is being called, and we'll run the binary. Here we see that main is about to call puts, and the next location that the instruction pointer will go to is hex 418660, which is the beginning of puts. And we can step right into it. Now, using GDB, I can also print puts, and we see that this is where the instruction pointer is at. The thing that is worth paying attention to here is if we run vmmap with the address of puts, this tells us that puts is located inside the /challenge/static binary. If we were to run vmmap with no arguments, this is all of the mapped virtual memory for the current running process. And we see that there is no libc mapped here. There is just challenge static. Now, if we were to do that same thing with a dynamically linked binary, we'll disassemble main, we'll set our breakpoint at main plus 9 here. I'm about to call puts from main, except now I'm not going into puts. I'm going into puts at PLT. And the assembly instructions here look a little bit different. This is that stub that we're talking about that dynamic linking uses. This is the place where the stub is located is called the PLT. Dynamic linking revolves around two tables primarily. The first we just saw. It's the procedure linkage table, also known as the PLT. The PLT is a table that holds short little assembly stubs that are responsible for resolving and calling external library functions. The second table that's involved is called the global offset table, or the GOT. And the GOT is just a function pointer array. What happens is the PLT will find an address in the GOT and call it. We can actually see the GOT in GDB here. If we have Jeff installed, we type GOT, and what we see here is that the GOT has two members. The first refers to puts, and the second refers to printf. And it is just an array of function pointers. So let's see how these tables relate. So on the first call to an external function, we don't know where that function is located. And so the address needs to be resolved. When the process starts up, all of the entries in the GOT are initialized to the PLT resolver address. Now what happens is our binary, our executable, calls puts. But this really goes to that stub, puts at PLT. Now inside of the stub, what it's going to do is it is going to jump to an address that is stored inside the GOT. And so we're going to have this type of instruction right here, a jump to RIP plus puts at GOT. And if we look at what's happening right here inside of our dynamically linked executable, as we step through this puts call, we get to the stub in the PLT. It's going to jump to whatever is at puts at GOT. Now this jumps us into the PLT resolver code. The resolver code is going to push a couple values and then jump. And so we're going to push, in this case, 0. We're going to jump. We're going to push another value. Then we're going to jump. Now, at this point, we are inside DL runtime resolve xsave. We don't have to know what this function is, but if we were to take a look at where we are, we are inside the loader, right? We're inside LD Linux x86 64. And so what has happened here is the executable called into the PLT. The PLT relied on the GOT entry, which said, we don't know where this function is yet. So we're going to go into the resolver code, and that is going to call into the loader. Now, once this resolution process of the loader is done, the GOT entry will have the address. We just trust that the loader here will figure it out for us. So if we were to take a look at GOT right now, we see that puts is this address right here. But this can't be puts. This is inside challenge dynamic. And so this address is that PLT resolver address. Now, if I continue execution and let all of this resolve, we're back inside of main. Now, if I look at the GOT, we see that puts now has been resolved and we have this address right here. If I were to print puts, puts is that address. And if we were to take a look at where in memory is that address, with vmmap, we see that the address that has been resolved is located inside of libc.so. If I run the vmmap command without any arguments, we see there's a lot more going on in memory in a dynamically linked executable. We have the binary itself being mapped into memory, we have libc being mapped into memory, and we have the loader being mapped into memory here. And all of these work together to make the binary execute. Now, once the GOT entry has been resolved and it has the correct address, in this case for puts, we don't have to go through this whole song and dance of resolving again. Instead, when our executable calls puts, it's going to go to that PLT stub, and it's still going to call this jump to whatever is stored in the GOT. But since the GOT now holds the address of puts, we'll go directly to puts, and we don't need to pay that resolve cost the second time around. We take a look at our main binary. We'll break at main plus 39, which is our next call to puts. We'll continue. And so now I'm about to call puts, but this time it's the second time we're calling puts. If I step through here, we're going to jump to whatever is at puts at GOT. And this time, puts at GOT is fully resolved and it contains the address of puts. So when I step one more time, I am immediately in puts. We didn't have to go and re-resolve this. And so we only pay that resolve cost once. So to recap here, before we've resolved anything, this is kind of the state of all of the parts that are involved. There is a puts call inside of the executable. There is a puts at PLT entry, and there is a puts at GOT. The puts at PLT is just a short number of assembly instructions that are going to jump to whatever is defined in the GOT. The GOT entry pre-resolution is going to hold the address of where to jump in the PLT resolver. Now, after we have gone through this loop and the function has been resolved, we still have puts inside of our executable, we still have puts at PLT, and it still contains a couple instructions that ultimately just jump to whatever is listed in the GOT. But this time, since we have already resolved it and we are post-resolution, the GOT entry now contains the address of puts inside of libc. So what are the consequences of this dynamic linking and resolution process? Well, let's think a little bit about it critically. There's some region of memory that contains these GOT function pointers. And because these have to be updated dynamically at runtime, that region of memory must be read-writable, right? So the page of memory where the GOT lives is writable. We can verify that here in GDB. We can run GOT. We can grab this address. If we run vmmap on it, what we see here is the page of memory is in fact read-write. Now, this leads to some very interesting exploitation paths that you may not have considered. Think about what would happen if an attacker could leverage memory corruption and control one of these function pointers inside of the GOT. What would happen if we change the address of puts to something malicious? Well, the dynamic linking kind of mechanism here is all about trusting the process. And so our main executable here is going to call puts, and that's going to go to the PLT stub. The PLT stub is going to jump to whatever is in the GOT. The result of this is we can direct control flow anywhere that we want if we can corrupt these GOT table entries. Now let's take a look at how corrupting the GOT can lead to an exploit. In order to do this, I'm going to launch this challenge again, except this time I'm going to do it in privileged mode. I'm going to run build sh on this GOT exploit source. Let's take a look at the source code. And now this has a little bit more going on, but we can ignore this top function here. This is really here if people want to play around in GDB and look at what's going on in memory. What we do have is a win function, which says this is never called in the program. And if we were to search the source for the keyword win, we see that that is in fact a true statement. The win function is never called. Now, if we follow the instructions here from main, the first thing the program is going to do is it's going to locate where the PLT GOT is. It's going to print that out to the user. It's going to print out where the win function is located. It is then going to read 8 bytes from standard in into that GOT table. We're going to overwrite one of those function pointer entries. It's then going to print read returned, and it's going to tell us how many bytes were read in. It's then going to say goodbye. So this binary is going to be named partial RELRO for reasons we'll see on the next slide. But if I were to run this executable, it prints out an address, it prints out a function pointer. If I hit Control D to send it 0 bytes, we see that it read in 0 bytes and printed out goodbye. So it behaved exactly how we would expect. Now, if I start passing in bytes, give it 6 A's here, and then hit Enter, we see that read returned 7. That's because it actually read in 7 bytes. It read in my 6 A's followed by the new line character, and we segfaulted. So how does an attacker take advantage of this? I'm going to use IPython. We can go from pwn, import star, p equals process partial RELRO, p send. I'm going to send that win address here, but I'm packing it to 8 bytes, and then we'll send a p interactive. If I run this here, we see we get the address of the GOT, we get the address of win, the read function or read syscall read in 8 bytes, and we have called the win function because it now says this is never called in the program. So we are able to call a function that was never called in the source code. Let's take a quick look at how that is happening. So I'm going to start the process, and then I'm going to have this input line, which says waiting to attach GDB. When I run the Python on the left-hand side, we've started up a process which has PID 331, but the Python script hasn't yet sent in any bytes. So Python is waiting for me to enter something, and the partial RELRO executable here is waiting for bytes to get sent by the Python process. On the right-hand side here, I'm going to attach GDB with sudo gdb a331. Because I'm attaching, I needed to be in that privileged mode. And so now I've attached GDB to the process. If we take a look at GOT, we see that there are, looks like what, 5 functions in the GOT table. And 4 of them have been resolved, puts has not. Now what I'm going to do is I'm going to type fini because we're currently inside of read in the challenge binary here. And so I want to continue execution until read has completed its job. Now I'll go back to my Python script and hit enter. And now we have passed in the 8 bytes to the challenge binary. Let's take a look at the GOT table again. Well, something's changed. If we scroll up a little bit here and look at the GOT, puts was resolving to 401046. But now that I've read in these bytes, I've overwritten the GOT entry for puts to 4011E6, which is the address of win. So the address of win is now what will happen when puts is called. If we were to continue stepping through this binary, we're going to call printf. Okay, printf worked perfectly fine. And that makes sense because printf was not overwritten. Now we get to the spot in the binary where main is calling puts. If I step into this, we're in the stub in the PLT, which is going to jump to that GOT entry. When we go one step past the PLT stub, we're suddenly inside of the win function. And when we continue execution, we're able to execute that. And so that is how an attacker can corrupt the GOT to make a program execute things that you wouldn't expect. Now, overriding the GOT is a strategy that's been around for quite a while. And so there are mitigations that prevent this from happening. The mitigation is known as full RELRO, where RELRO is shorthand for relocation read only. The strategy isn't that complicated if you think about it. What full RELRO does is it forces the loader to resolve all of the entries in the GOT before main is even executed. And not only are they all resolved, but that page of memory that used to be read-write becomes read-only. And so we can no longer overwrite these pointers. That is why our challenge binary over here in our demo was called partial RELRO. You can check if a binary has partial or full RELRO by running checksec. So if I run checksec on this binary called partial RELRO, we see that there is partial RELRO. Partial RELRO makes some of the GOT read-only, but it doesn't impact what we talked about in this lecture. There is either full RELRO or we can perform this type of exploit. Now, you can enable full RELRO just by adding an additional compilation flag. If we take a look here at build RELRO, we see there's a few more flags I have to pass to the linker to make this happen. but we can run build RELRO on our GOT exploit. And then if we check sec our full RELRO executable, we'll see that it now has full RELRO enabled. Let's try and perform our exploit one more time. We'll attach GDB here. All right, if we look at the GOT entries, they're all green. Even though we haven't called puts yet, puts has been resolved. And what's more than that is if we were to take a look at the page of memory that corresponds to where these function pointers are located, it is now read only. And so if I were to run this, we see that read return -1. We encountered an error trying to read bytes into read-only memory. We weren't able to overwrite these values. And so we were not able to call the win function. We just got read return -1 and goodbye.